Excuse me, ma'am.
Yes,
Ma'am, we've gotten a few slides to share, just a few slides to share. So, for a couple of minutes, we will be kind of sharing those slides, ma'am. Could you please share it after that?
yes. Okay.
Yeah, thank you so much. Thank you, ma'am. A very good evening to our esteemed speaker, dear participants, and fellow members of Nebula Pioneers. Your engagement tonight underscores the spirit of knowledge and excellence that defines our community. As the stars begin to twinkle in the night sky, we gather here to embark on an extraordinary journey to delve into the wonders of space robotics, a field that is at the forefront of our quest to explore the cosmos. In the serene evening setting, I would like to start by expressing our profound gratitude to our esteemed keynote speaker, Dr. Shreya Santra ma'am, for graciously accepting our invitation. We are extremely honored to have you sharing your insights into the intriguing field of advanced space robotics, the frontiers of space exploration. On behalf of Nebula Pioneers, I extend a warm welcome to you, ma'am. Now
Thank
let
you.
me take Thank you, ma'am. Now let me take a few moments to give you a short intro of our club. At Nebula Pioneers, our mission is to foster a passion for space exploration and technology. Today's session is a part of our ongoing effort to bring insightful and forward thinking discussions to our community. We are a team of passionate individuals united by shared thirst for unraveling the cosmos' greatest mysteries. We specialize in the field of space science, astronomy, theoretical physics, mathematics, and computer science. So why join us? Stay up to date with the latest space news with stunning infographics that will be delivered every single day in our club. You can also participate in guest speaker sessions like the one you have now, and you will also be able to participate in some hands-on workshops and cosmic themed quizzes. You can also connect with few space enthusiasts like you for some thought-provoking discussions and knowledge sharing sessions. You will also find our club's social media handles in the chat sections. Please don't hesitate to join us. Now, I would like to welcome Karan, the founder of Nebula Pioneers, to share a few words.
Hello. Thanks, Kamla. Good evening, everyone. I hope you all are doing well and feeling excited for today. As we are here embarking on this incredible BS degree journey together, amidst of all the hustle and bustle, here we are having a place where the passion for space could thrive and connect with others who share the very same excitement for exploration and space. Nebula Pioneers is not just a club. It's a warm, welcoming space for all the enthusiasts. Whether you are a seasoned expert or just getting started, we are here to learn and grow together in this degree and like dive into it. What can you expect from Neurobinos? Endless possibilities are there, from lively debates to fascinating science talks, collaborative research projects, expert sessions, golden podcasts to movie nights, and much, much, much more. Under the stars, there are some, not something, there are many things that would be there. Don't worry about the fitting it into your busy schedule. We'll make sure to find time that works all for you. Let's embark on the cosmic journey together. Welcome to Nebula Pioneers. And I would like to uh, extend a warm welcome to our guest, Shreya ma'am. We are looking forward to for her insight and experience, expertise. Thank you.
Thank
Thank
you,
you,
Karan.
Karan, for your inspiring message. It is with great excitement that I now introduce our keynote speaker for today's session, Dr. Shreya Santra ma'am, a renowned expert in the field of space robotics, recognized as the IAF Emerging Space Leader 2024. Dr. Shreya Santra ma'am serves as an assistant professor in the Department of Aerospace Engineering at Tohoku University, Japan. Her work specializes in coordination, control, perception, and motion planning for multi-robot systems utilizing advanced algorithms to operate in challenging and unstructured environments. She is also the recipient of the prestigious scholarships and awards from MEXT Japan and DAD Germany for her groundbreaking research. Her current focus on research is on applying AI and deep learning techniques to multimodular planetary robots. She also holds a PhD from Space Robotics Lab, Tohoku University. We are truly honored to have you with us today to share your insights and expertise on the advancements and future directions in space robotics. Please join me in extending a hearty welcome to Dr. Shreya Santra ma'am, who will now lead us through her fascinating insights. Over to you, ma'am.
Thank you, Kamla, for the very nice introduction. And thank you, Karan, also for the nice introduction to the club and what you all do. So I'm very happy to be here today and for inviting me here to share about space robotics, something that I am very passionate about. So as Karan mentioned, most of us are here because of our passion for space science and space tech and some related to space, and whatever I am now is because of my passion for this field. And I did my BTech in electrical and electronics engineering at NIT Jamshedpur, and then on went on to do my master's in space studies and engineering, and then I did my PhD in space robotics. So I worked on different kind of space systems, including satellites, and now on space robotics. So and the most that I love is space robotics design and development. So I'll talk about that, what we do and what why we do that. And if you have any questions, you can write it on the chat, or we can take it at the end. So can I start? Uh, Share, like,
Yes, sure, ma'am.
okay, thank you. So today's agenda will basically be introducing what is space robotics, what are the challenges in this field, what are the research and development that's ongoing, and what are the future of space robotics. So if someone of you have attended my talk before, you might find something similar, but I kind of customize the talk so that it can cater to those from data science or from interdisciplinary kind of background. So it's not very technical, but it's also not very general. So you'll see. Coming to the applications of space robotics. So robots, as you know, are applied in multiple sectors on Earth. So they can be employed in the nuclear power plants and disaster sites, in medical and in war sites, disaster response and stuff like that. So basically, employing robots where humans cannot go, or it's dangerous for humans to go, is something that really makes a difference. And space is one such environment where it's the extreme environment, the high temperatures are very difficult for humans to operate. And so if we can employ robots in this kind of environment, we can do several tasks like deep space exploration. We can do a survey of planetary surfaces. We can do assembly and construction tasks, service and maintenance tasks, and also automatic or autonomous robotic landings can be done by these kind of employing robotic technology. So before we get into the main crux of the presentation, I want to have a short trivia. You'll have like 2 seconds to type your answer and or 5 seconds to type your answer on the chat. And if you get it right, I'll call out your name. Yeah. So can you name some of the first space robots ever deployed? You can write it in the chat if you know the answer. Name of some of the space robots ever deployed. Okay, I see some answers coming here. Curiosity, Perseverance, Sputnik 1, Mars rover. Okay. I'm not aware of TARS. Venera, that's great. Yes. Mihir Chakrade has said about Venera. Okay, so your time is up. Yes, so space robot is not a new topic. It has been here since the 1950s, 60s. Due to the space race between USA and USSR, robots were deployed on the moon, to Venus, to Mars, and everyone wanted to be the first to send their technology to these celestial bodies. And that's how it began. And the very first ones were this Luna Code series, which were basically rovers that were landed on the surface of moon in the 1970s. And Luna Code 1 was a very successful rover that traveled several kilometers on the surface of moon by teleoperation. And then there were Viking 2 by the USA. Luna Code was by the Soviet Union or USSR. Then Venera, someone called out Venera. So Venera had a series of spacecrafts. Many of them failed, but Venera 9 actually landed on the surface of Venus, passing through the dense atmosphere of Venus and sending us data. Then there was the Mars series of landers that landed on the surface of Mars and did some scientific research. The Viking 1 and Viking 2 landed on Mars as well. Viking 2 even had a robotic arm that could collect samples and do some kind of analysis. Then that was in the 1970s, but later Robotics, that was a orbital robotic arm that was sent on board the Space Lab mission on a space shuttle, and it demonstrated some in-space manipulation using this 6DOF arm. So that was in 1993, and since then in 1990s, several rovers were landed on the surface of Mars. So it goes back really like really back in the history of how space robots came in. So if you're thinking about Curiosity, Perseverance, those are very recent actually. And Sputnik 1 was not a robot. Sputnik 1 was a satellite that just kind of beeped back some communication signal. A robot is something that can do some kind of manipulation or locomotion kind of tasks. So as you see here, the Luna Code or the Robotics or the landers, they did some kind of task that could collect some samples, do some kind of analysis. So that way it becomes a robot. Now, and satellites can also be robots if they have some kind of manipulation, and we will see how that happens. So coming to the question of why robots, as I mentioned, space is hostile. The extreme temperatures, microgravity, meteorites are very difficult for humans to work. And also they have to get all these kind of protection gears that will like kind of hinder the way how humans should work in these kind of infeasible locations. And instead of sending humans, if we send robots, it reduces the risk of the missions, and also like the cost of the missions. So getting humans in space is a very, very costly affair. It requires years of development and testing and safety protocols and a lot of uh, policies, law. So compared to that, robots are much more easier to send. And of course, mental state. We all know that humans are social animals, and we need our way to relax and to be with people we love. And so long isolation can really affect our mental state. And that way, robots are practically not affected by these kind of long isolation periods. So these are some of the reasons why we should and why we do deploy robots in space. So coming to the categories of space robots, one part is the orbital robot, the other part is the planetary robots. So orbital robots are those that operates in the orbit or in microgravity conditions. So as I said, like if a satellite has a robotic arm, or if it has some kind of manipulation where it's able to do some kind of maintenance or refueling or space debris removal, then it becomes a robot. And also if it's able to do some kind of research, like on board the space station, there are several free floating robots that do experiments, take pictures, assist the astronauts. Someone called out Robonaut 2. So yeah, Robonaut 2 was a orbital robot as it was working inside the space station in a low gravity orbital environment. And coming to planetary robots, these are basically robots that are sent to celestial bodies where they can become probes for scientific exploration, or basically trying to set up some habitats or facilities or infrastructure for future human missions. Coming to my work and my what our lab does, we are the Space Robotics Lab, and we work on different kind of topics like orbital robotics, limb robotics, wheel robotics, terra mechanics, and hybrid and modular robots. So the lab was started in 1995 by Professor Kazuo Yoshida, and since then we have been developing several kind of robots that have been also sent to space, like Hayabusa 2 was developed here, and also the lander by iSpace, we contributed to them. We also worked with some of the rovers by iSpace company. So these are like different kind of robots that we have developed, and of course we focus a lot on R&D, trying to figure out different kind of challenges that exist for space robots and how we can solve them. So some of the challenges for space robots are listed here, as you can read through them. However, we do not like go through all of them, but we try to address some of them, like efficient robot designs, mobility, guidance and navigation, science payloads and experiments, how we can have multiple teams of robots or swarm robots, and how we can solve the issues in these kind of team of robots, and how we can have more and more autonomous capabilities. So these are some of the research topics that we deal with. But as you know, like as we design robotic systems, we also try to look into the challenge of mass and power limitation. So in space, the resources are very limited. So you cannot send heavy things. You cannot send you don't have unlimited power. So you need to consider your robots such that they can operate in these kind of limited resource environment, and also how you can get it tested and qualified for space, how it can be protected from harsh space environment and things like that also comes into play as we do these kind of research. So today I'll go through all of these R&D points that I mentioned just before this. Coming to efficient robotic design. So when we design a robot, it's very important to understand where and how these systems will work. So what is the mission goal? What is the mission timeline? And how redundant they should be, how robust they should be. So these are very important, and how they can move around, what is the mobility, the manipulation, tasks that they need to do, how much of autonomy they should have, what kind of instruments will be on board. So these are different kind of things that we need to consider when we design robots. And here I've just put some pictures of different kind of conceptual robots. These are not robots that have been sent to space, but more like in the design phase when you have to consider what all tasks that they have to do. So coming to some mathematical representation of how we design the robots is like, if, for example, if we are designing a manipulator that can work in orbit or on the surface of another celestial body, we need to consider the kinematics and dynamics of such systems. So you need to consider what is the degree of freedom, what is the actuation needed for the specific application. And especially when the manipulator is operating in an orbital state, so in a free floating state, the position and orientation of the base of the manipulator fluctuates. And so there is a lot of vibration, there's a lot of like moment, force and moments that are applied. And the main task is you have to do the conservation, apply the conservation law for the system and make sure that all the dynamics are proper. So this is a general equation of the Jacobian matrix and how you can solve for the different parameters that we consider for designing ARM, for example. So this is in the book called Handbook of Robotics, and the chapter is Space Robotics, page 1044. It depends on the edition, but yeah, this is the second edition where the Space Robotics chapter, they clearly define how we can design a manipulator for space. So this is an example. So basically how we have to consider the different forces, the different moments that are acting on this system. Coming to mobility and locomotion. So there are different kind of mobility and locomotion depending on where and how they are going to work. The most common one is the wheeled robot. So most of the rovers that you know, rovers meaning roving on the surface, have wheels. So different kind of robots are designed that can move on wheels, because this is, they can at least move on kind of unstructured but also flat or more hard soil or hard land. However, if you want to go into the caves inside, or if you want to climb hills, or if you want to climb ceilings, rovers cannot do the tasks. So then you have to design some kind of legged robots, robots that can grasp and move, or hold and move, or these robots can be inspired by animals, or these robots can be inspired by insects based on what kind of environment that they are working in. Then there are flying kind of robots. So you might already know the NASA Ingenuity helicopter. That was the first flight of Earth. So NASA demonstrated that we can fly robot on Mars, and that was a very, very successful mission where the robot Ingenuity would fly around and take pictures, and it even helped in the path planning of the wheeled rover Perseverance. So flying robots are possible where the atmosphere are a little more dense. Coming to tumbling kind of locomotion. So if you're going to a microgravity area, so like an asteroid where the gravitational pull is really low and you cannot stay on the ground for too long, nor can you fly around. So you need to have a kind of mechanism where you are tumbling or bouncing on the surface such that you don't apply too much force on the surface and you don't get thrown out. So this is a simulation of the mascot robot that was landed on the surface of asteroid Ryugu, and it basically moved around by changing the center of mass of the robot from one point to another. Then we know that some of the celestial bodies like Enceladus and Europa, they have water under the surface. So you might have oceans under the surface, and this kind of requires some kind of robot that can float or be buoyant, so that it goes under the water and it can inspect inside the water. So scientists are even developing these kind of robots which can float in these oceans and can be sent to Enceladus and Europa. And similar kind of robots are being developed, inspired by reptiles, for example, geckos or snakes, so that they can slide around on these icy planets or icy bodies and inspect around the surface. So these are some type of locomotion, but you can also have hybrid locomotion. So this is the rover or the robot that is designed by DLR and the German Aerospace Agency and the French Aerospace Agency. And this is going to this moon of Mars. So the natural satellite of Mars called Phobos. And again, the gravitational pull in this body is very, very low. So we don't know how it's going to work. Is it going to hop? Is it going to move around as a rover? Or is it going to like walk? So they have kind of implemented all different types of locomotion. So it also has wheels, and these legs can even stomp and walk. And as you saw, it landed as a box, so it can even tumble around. So these you can also have a hybrid locomotion, that because you don't know what is there in the unknown environment. So the main thing that we consider when doing the locomotion and mobility is the interaction between the limb or the wheel with the soil or the terrain where it's going to operate. So this is called terra mechanics. It's the study of mechanical behavior of soil or terrain and its interaction with the vehicles or the structures moving on it. And this is important because if we don't understand how this interaction is happening, we will eventually lose the robot that's operating there. So it happened during the Spirit mission. So Spirit was the rover on Mars by NASA, and it actually got stuck in the loose soil, as you see here. And after several weeks of trying to get out of that soil, it could not get out, and it just got stuck, and then eventually it lost all the power and the mission was ended. So this is very important that we understand what kind of terrain the robot is going to move on and test it for different kind of scenarios. So test it for loose soil, test it for hard soil, test it for what is the amount of slippage, what is the amount of sinkage that are happening based on these kind of soil characteristics. So here is the wheel of Curiosity. So Curiosity rover was landed on Mars in 2012, and since then it has been operating. And you can see how the hard rocks and terrain of Mars has damaged its wheels. So here you see Spirit is also on Mars. It was loose soil, it got stuck there, and Curiosity is on Mars as well, but its wheel got broken. So these are very important things that we need to know before we send our robots. And this is our rover that we are testing in a loose soil sandy dune for our field test, trying to understand what is the slippage and sinkage at different speed. So that was about that was about the wheels, but we do the same kind of testing for legs and legged robot as well. And for example, what is the reaction that the robot legs experience when it's trying to grasp a surface? And then we test it on different kind of environments. So here you see a test bed that we have where we try to do a offload test. You can see a string is attached here, and the string kind of creates a microgravity condition where it's pulling up the robot, and the robot is trying to grasp on the objects and then moving. And here on the top right is the International Space Station mock-up, where we are testing our robot to hold on different rails that are on the ISS and trying to move around and that take pictures or do fetch something for the astronauts. So that was about mobility and locomotion. Coming to the next challenge is guidance and navigation. This is very, yes, yeah. So guidance and navigation is important because we need to know where the robot is going, how it is going, is it in the right path, and things like that. So first comes the perception, where you have to understand the environment through different sensors. Usually, most of the time, it's the camera sensors, the visual sensors, where the robot tries to take pictures of all the things that are around the robot. And then it tries to understand if it's at the right place. So it localizes itself. On Earth, we have GPS and we can understand where we are, where we have to go. But on Mars or Moon, we don't yet have this kind of infrastructure or facility. So we need to know where the robot is, and that can happen only by kind of identify different kind of features and then coming back to it and seeing if that feature is still available, and then you try to localize itself. It's called interloop closure or intra-loop closure, where you basically try to go from one point, you collect all the different features, then you keep mapping, and then you come back to the same place where you started, and then you do a map correction. And this way you kind of understand if you followed the right path or if you drifted out of your path, and if you were able to map the area correctly. So this is called SLAM, simultaneous localization and mapping, and it's a very, very important system that's basically deployed on robots. And it takes up information from different kind of sensors like the camera, the LiDARs, even the wheel odometry, the IMU, and these kind of data are all fused together and then used for localization and feature matching. And then comes the control. So once you know where you are and how you need to go, you try to like form a trajectory of the robot. So you have some information from the orbiter. So usually we get this data from orbiter of Mars or orbiter of Moon, such as like the Chandrayaan-2 has a very good camera on board, or the Lunar Reconnaissance Orbiter by NASA, they have a very good camera. And these camera images can be taken, and you can roughly plan a path of where the rover is supposed to go or where the robot is supposed to go. But this data is not very accurate because they are taking it from the orbit. It's still not very high resolution. So the robot should still be able to have some kind of onboard path planning and have a local path planning, and then accordingly control its actuators to move to that distance. So it's called global and local path planning, and most of the times these both of these are fused together for our robotic path planning and task planning as well. Then if we have to go to the very like unknown places like caves or like skylights or lava tubes, then we absolutely have no idea about those places, like because the orbiter cannot really take pictures inside these caves. So it's completely onboard data that you have to rely on and path your plan. So that way you have to be very slow, very cautious, or have the robot have like the autonomy to decide which obstacles to avoid, which obstacles to overcome, and which obstacles or which things it can sample or collect. So coming to sample collection and analysis, this is of course very necessary because you go to these kind of remote celestial bodies not just to take pictures. Of course, pictures are very important, also scientific outcome, but also you have different kind of scientific instruments on board these robots, and they do different kind of science, like for example, the Chang'e lander that was by China, they had excavator arm, the drilling machine, a lunar penetrating radar, all these kind of things where it would collect sample, and then it was a sample return mission. So it would collect all the sample and came back to Earth. And then it like this left bottom is a kind of laser or radar penetrating instrument on board the Perseverance rover, where it tries to analyze the composition of rocks on Mars. So these kind of techniques are important. And as I was saying, the Hayabusa 1, which went to the asteroid Itokawa, was designed in our lab by my supervisor back in 1990s or early 2000. So long back. I wasn't involved with that, of course. So what he designed was this sample collection mechanism where it would a small pellet would be thrown down, and that would cause eruption of the dust of the asteroid, and then that dust was collected and then it was brought back. So asteroids are low gravity bodies, so you cannot really have something there for a very long time. So as you can see, it's touching for a very less time, and then it's just collecting and coming back. So these kind of sample collection, and as well as onboard instrumentation. So these all of these instruments are on board one of the rover currently in space. Do you know which robot are these part of? Anyone? So it's a infrared spectrometer, thermal infrared spectrometer, then even MOXIE, cell lock. Yes, Mars 2020. So Saidatta Shri has rightly answered. All of these are on board the Mars 2020 Perseverance rover. And basically, the Perseverance rover is considered a geologist. It does its own science, it does its own analysis, and then it sends back the results. So coming to the next trivia question, again, you will have 5 seconds to type. Can you name some recent current space robotics missions? One is, of course, Perseverance is already written. Changi 6, awesome. Yes, Changi 6 is a very successful mission. Osiris Rex, yes, Mihir. Anyone else? Chandrayaan 3, yes, absolutely. So these are some of the current or recent space robotic missions. So Perseverance, of course, Curiosity is still functioning, current. Then there is Dexter arm on board the space station. There is the GEM RMS also on board the space station. These are manipulator arms, and they can do a lot of tasks in space. They kind of capture the astronaut capsule. They even like release satellites, they release different kind of robots and or do different kind of tasks like cleaning or solar panel assembling and things like that. So these are very important robots as well. Then the Geet Eye robotic arm was inside the space station as a to help astronauts. U-2 by Chinese Space Agency on the Moon, and Zhurong also by Chinese Space Station Agency on Mars. And of course, Chandrayaan 3, our very own Chandrayaan 3 that was landed last year, the lander and the rover, which Vikram lander and Pragyan rover. So of course, that's a very major mission. Changi 6, someone said, yes. Osiris Rex, yes. Hayabusa 2, yes. These are not current, yes, but recent. Then, yes, Lev 1 and Lev 2 by the Japanese Aerospace Agency, as well as the lander by Intuitive Missions, Odysseus. And yes, the DART mission as well. So because everyone is so excited about Chandrayaan 3 and myself included, I wanted to have one specific slide dedicated to Chandrayaan 3 and what its mission objectives were and what it achieved. So it's, of course, a very phenomenal mission by India, and we kind of showed that we are capable of doing safe and soft landing on the lunar surface and even drive a rover on the surface and do in situ scientific experiments. And all of this was done by very economical and minimal instrumentation, and the mission itself was very, very phenomenal. So, and they even demonstrated that the lander can hop and move to a different location, kind of showing that it's possible to do a sample return mission where the lander can again come up from the surface of Moon and come back. So Chandrayaan 4 is actually a planned sample return mission that will happen soon. And the rover itself, the Pragyan rover, it had different onboard instruments and the guidance, navigation, and control system, where it would travel over few kilometers, and also it has kind of one of the highest records of traveling the most number of kilometers or largest distance in a lunar day, like 14 days. It has covered quite a lot of distance and it's set a record. So coming to the fifth topic, which is the swarm, or the third topic, which is swarms and modular robots. So all of this time I was talking about single robot and how they are being controlled and how they are already in space and how they are being navigated. However, most of these tasks can also be done by multiple robots that can work together and do the task like the slam I mentioned. If instead of starting from one point and coming back to the same point, if we have multiple robots that are mapping their individual environment and at the end they kind of merge the map, then it becomes even more correct. The map becomes accurate and you don't have to spend the extra distance of coming back to the same point to merge your map. So it's called interloop closure between the different agents, and this whole thing is the collaborative SLAM. So the main idea is multi-robot systems can work in a collaborative manner depending on the tasks that they are assigned, and then they can actually work in centralized manner or decentralized manner or distributed manner. So centralized manner meaning if you have a lander, which is basically sending commands to all the different robots around it, that's a centralized. But the most robust way to operate is decentralized or distributed manners, where you don't have a lander to control the agents. Rather, each of the agents are autonomous, and then they can kind of explore the area by communicating with them among themselves and collect information and sending data to the lander wherever possible. So that way, if the agents are working in a distributed manner, they can decide which areas to cover. They can kind of avoid collisions. They even like if you know how swarms of ants or swarm of bees work together, they kind of collaboratively try to do one task. So in this simulation, the task is to cover a given area in the fastest time or the shortest time possible, and that's what they're doing in the most optimized manner. So in swarm planning, we do try to implement different kind of optimization and task allocation, where the robots are traveling in distributed manner, and then they just share some information. Like on the right is basically showing communication links between the agents, and at every point wherever they are able to set up a communication link, they can send information and see what to do next. So that was swarm. And coming to modular robots, as we all know that I mentioned that the in space the resources are limited, so you cannot really send large masses or large components up. So you need to send smaller components or modular things that can be attached together and do different tasks. Even the International Space Station was built in the same way. Several missions took different modules. The modules were attached together, and then the whole space station was built. So when we plan to have infrastructure on the moon or Mars, we cannot have all together. So what we can do is send different modules that can be reconfigured, and the design can be interchangeable, and we can do different kind of tasks. So here you see a picture or conceptual art made by our students, where we are trying to see what different type of modules we can make and what these modules can do when they are attached with each other. So this is just a conceptual sketch, but mainly what we want to do is be versatile and robust and adaptable to the change of environment and tasks. So to realize this kind of vision, we started working on this kind of modularity where you have different kind of locomotion based on the module that is attached to it. So here the basic module is the leg and the limb and the body. So if a single leg is attached to the body, then the robot moves in a specific locomotion. And then if this here you can see my student attaching the second leg, and then it moves in a different kind of gait pattern and so on. So it recognizes the number of legs that is attached to it, and then it tries to generate the leg pattern. And this is autonomous. He's just attaching the limb and facilitating or putting it like here. For example, he makes it stand and then it starts moving in a different kind of gait. So, and here when he changes a leg to yeah. So he changes the leg to a manipulator arm. Then it changes the thing that it has to do. So it doesn't start moving, rather it starts moving like shaking the arm. So it kind of understands what configuration it is in. So it's important to have this kind of modular self-recognition and reconfigurable robots for future. Coming to autonomy and intelligence. So all of this, the perception, the guidance, the navigation part, so far have mostly been done by teleoperation. But gradually we are moving towards more and more autonomy on board these robots. As you saw, the modular robot, it basically understands what its configuration is and then does autonomous gait. So here what we try to do is it sense, think, and act just like a human would do. So this is how we sense through our sensory organs, we think with our brain, and then we act with our limbs and execute the motion. Similarly, robots can be in a same type of nervous system where it can sense using all the different sensors on board. Then it can think using the main microcomputer or whatever autonomous computer that you provide to it, and then it can act accordingly. And one of the things that we are now focusing more and more is reinforcement learning and imitation learning. So reinforcement learning is nothing but if you imagine a human baby, since the baby is born, they perceive their surroundings, they observe what others are doing, and gradually learns as they grow. And is not just by observing, but even by their own actions. So similarly, we can do the same for robots, where they are given a reward for a specific task and penalty or punishment for a specific task, and then they learn from these rewards and penalty, and they know what they should do. And we are focusing on this kind of learning based control and locomotion of robots. And imitation learning is where it can learn from other agents, whether it can be another human or it can be another robot. So as I showed, like if we have multi-modular robots, we need to assemble them, or they can assemble themselves, and then they need to learn from each other. You can have some preliminary program on them, but they basically have to learn from each other, and that's how we can implement imitation learning between the agents. Coming to also like perception and navigation, how we can implement autonomy in here is, of course, machine vision. As you all know, machine vision is one of the very powerful AI tool where the robots can use their capability to recognize or segment what it's perceiving around. So instead of just saying that, oh, this is an obstacle that I should avoid, it can actually understand that it's a smaller rock or a bigger rock or another rover. So if it's another rover, it might have to go near it and communicate with it, or if it's or avoid it, depending on what kind of scenario they are in. So we do a lot of machine vision, and someone even asked if we do training and simulation. Yes, we do a lot of training, both for the machine vision, but also we develop these kind of photorealistic simulator where the robots are trained in these kind of simulators that look very similar to the environment of Moon and Mars. So then you can train them in this kind of like generated synthetic images and then put them in the real world or in an analog site and test if the model that you developed is actually correct or not. So here on the left that you see is actually the simulator that we have developed. It's called Omni LRS. It's developed on NVIDIA Isaac Sim. And this on this environment, we train our robots for navigation, for detection, obstacle detection, and segmentation. And on the right bottom, this is an analog site with our collaborators where we put our rover that was trained in the simulator, and then we see how well it has been trained and how well it's been able to detect all the different obstacles that are around it. And the result was pretty good. You can check our paper. It's on ICRA. I did not put, I'll share it on the chat later. Yeah. And then as I was saying, like imitation learning, where the robot learns from another agent. Here on the left, you saw that the student put the leg and then it starts moving. And then the same thing the manipulator does. It picks up a leg and then it puts it on the modular robot. So this is a preliminary task that we did, but now we are trying to develop this, how the robot can recognize what the human is doing and how it should perform the same task. So all the thing that I mentioned about autonomy and intelligence and sample collection, all of this can be done by people like you who are working into data science and engineering kind of background. So things that we do are predictive modeling and navigation. This can be done much better if the models are data driven, and you can build robust models for perception, control, and navigation. You can do resource optimization of power and computational capacity. You can understand and interpret the sensor data in a better way if you are trained in data science and analysis, and also simulation and training, where you create realistic images in these kind of simulators and then prepare the robots for real world missions. So yes, you again have like 5 seconds to answer. Can you name some of the future space missions? So we talked a lot about AI and autonomy. How do you think these future missions will have more and more AI on it, and what are those robotic missions? Okay, Gaganyaan, Shukrayaan, Mom 2. Chandrayaan-4, okay. Viper, yeah. Cancel, yes. Okay, so 5 seconds are over. Someone mentioned Gaganyaan. I'm not sure what kind of robot will be on board Gaganyaan. Yes, there is Vyomitra, but I don't know if it is the objective is to manipulate or do some kind of task or just for scientific radiation studies. So Gaganyaan, I'm not sure. Mom 2, again, it's on the orbit. It will just collect orbital data and pictures. Shukrayaan might be a robotic mission. Chandrayaan-4, yes, absolutely. Chandrayaan-4 is going to be a sample collection and return mission. So that's, of course, Lupex. Mm, One of the thing is Viper was canceled last week, but it's still going to happen. Like they are going to sell it probably to some commercial companies and then eventually redesign it and maybe send it to the surface of moon. And it's a very unfortunate thing that it was canceled. It was going to be a very groundbreaking robotic mission. Um, but sad. Then, as I mentioned, MMX, Martian Moon Exploration, it's a joint space robotic spacecraft by Japanese Aerospace, German Aerospace, and French Space Agency. So that will be going to Phobos in 2026, hopefully. CADR mission by NASA is a very, very interesting mission where it will have 3 small robots on the surface of moon, and it will collect data, like it will connect some radar information of the surface of the moon, and it will also communicate between each of the agents and do some path planning and work in a distributed manner, as I showed you in the previous slides. So that I'm very excited for this mission if it happens. And Dragonfly mission by NASA is going to be, it's kind of approved, and it's going to Titan, the moon of Saturn, and it's a octacopter. So it's going to fly in the atmosphere of Titan because Titan has a very dense atmosphere, and it can fly over there. So these are some of the future missions that are happening, and most of it are going to be autonomous. Even the Perseverance rover is very autonomous. Like 90% of the distance that it has covered has been autonomously and not by teleoperation. So as you go in the next decade or so, more and more space robots are going to become autonomous. And that's where it comes how you can be part of this entire field, because the space robotics market is growing in a very rapid fashion. It's still very dependent on the national space agencies and government, but there are so many companies that are coming up that want to build space robots for these extreme environment, and these are some of the companies that are listed here. And some of my favorite ones are iSpace and Gitai and like this intuitive machines. They're doing really well, and they are already like qualified their robots for space, and iSpace is going to land or launch their rover later this year. So it's very exciting times for space robotics. And how you can stay in the loop is you have to develop, you already do a lot of programming, and you have this kind of logical and systems thinking attitude, which is basically important to have because that's what your autonomous robot should be able to do. So you should develop that kind of skills that your robot should do. So judgment, decision making, logical thinking, and different kind of programming languages and different kind of softwares that will be useful for having for designing and developing these space robots. And if you are interested in simulation platforms, it's a very big growing field because you cannot have robots to go in analog sites or go directly send them to space. So instead of that, you can develop photorealistic and more physics-based simulators that can help you to train the robots before they are actually deployed on the hardware and tested in analog sites. And if you are interested in studying higher in this field, I've kind of made a list of uh, colleges that teach space robotics and extreme environment robotics. And if you scan this code, you should be able to find the list. So you can reach out to the professors or you can reach out to the institutions and apply for master's and PhD. And on the left are basically some organizations that are involved in doing space outreach, not research, but space outreach, just like Nebula Pioneers. So I think in this list, I will add Nebula Pioneers for my next talk. And yeah, be informed, stay in the loop, and be passionate about this field. And I want to end my talk by saying that robotics is a very fascinating subject that's very interdisciplinary and the need of the hour. So a lot of people think that AI is replacing jobs, AI is taking away their uh, livelihood, but that's not true. Actually, to build a robot, you need so many skilled people. So it's very important that you develop the required skills, which your robots cannot ever acquire. So if you are skilled enough, no one can take away your job. So yes, the future is for robotics, and space robotics is really, really exciting. And I hope all of you were inspired and got interested with this talk. And thank you so much for your time. And yeah, if you want to connect with me, I'm on LinkedIn and ResearchGate, and I also have a website. So you can look out for me. So thank you. I hope I was not too late.
Yes, ma'am. Thank you, ma'am, for that enlightening presentation. We are grateful that you mentioned our club in your talk. So thank you so much. It really means a lot for us. Your profound enthusiasm for communicating the advanced technologies and also the future opportunities in space robotics, your commitment to sharing this knowledge with us today is remarkably inspiring. Thank you so much, ma'am.
Thank you. Thank you for your time. I'm open to taking any questions if you have.
Yes, sure, ma'am. Following this, to facilitate the Q&A session and address the selected queries, I would now like to invite Agamani and Raju, the co-hosts for today's session, to take over.
I don't see any questions in the chat.
Raju, hello.
Hi.
Hi,
Uh,
am I audible?
yeah, yes, you are.
Okay. First of all, good evening, everyone. Good evening, ma'am. Uh, at first, I would like to invite our audience. If you have any queries related to the topic discussed, please feel free to post them in the chat box. And we kindly request Sandra, ma'am, to address any question or concerns raised by the audience. Dr. Sandra, we have a few more questions from our audience that have been collected uh, during the registering the form, and they are wait a second. The first question is, ma'am, how can robotics be integrated with satellite and space stations for effective space exploration?
Okay, I think I already covered that. As I mentioned, space robots are two types, orbital robots and planetary robots. And orbital robots are robots that can be satellites with some manipulation capabilities. So robots that can have arms, for example, for refueling or maintenance, or let me show you a picture. Okay, maybe this one. So here, uh, yeah, here this picture that you see, this one is actually a robot that we have built, a satellite robot with manipulator arms that can capture fast moving debris or fast spinning debris. And this is a test bed, 2D table test bed where the robot can move in a free floating fashion and try to capture the spinning debris. So that's one way. The other ways are, of course, having long manipulators that can do refueling and servicing. And like the space station already has manipulators for capturing capsules or releasing satellites. I already mentioned that.
Yeah.
That's that.
Okay. And the second question is, how can a mechanical engineering graduate or a postgrad delve and work in the advanced robotic fields? Can you any particular skill or certificate course give them, and as to make them industry ready?
Okay. So mechanical engineering is a very, very important skill that is required for efficient robot designs. The better you are, the more innovative way you can think about designs, uh, that would be like amazing. So if you can design different kind of modular robots, different kind of um, like shape changing robot or origami kind of robots, these are mostly done by mechanical engineers. And of course, other than that, mechanical engineers also look into different kind of materials that can be implemented in these robots. So of course, materials engineering, but also mechanical engineers have to have that kind of skill of what kind of robot materials that you can add in your um, robot. So in case of certificate course or certifications, I am not aware of it because I feel more than courses and more than certificates, the important thing is doing hands-on. So if you can design different kind of robots, if you can think out of the box, if you can make them by 3D printers, additive manufacturing, or even in your workshops, you can actually do the dirty job of building the robot. That's what makes you more skilled than certifications. So yeah, if you have a mechanical engineering degree, that's great. But if you can do actual robotic projects, actual building of the robots, that's what makes you a mechanical engineer.
Okay. And the next question is it more beneficial to send out humanoid robots to space given the limited technological infrastructure, and LLMs are computationally expensive process?
Okay, I'm not sure if I understood the entire question, but yes, humanoid robots first going to space station or to Mars or Moon would definitely be more beneficial than sending humans first. So as I showed, like if we can have modular robots that can build up themselves, even if not like humanoid, but more like bipedal robots, and they can do the tasks that are required. That's really good, and that's the way that we should go. And LLMs are being implemented on robots anyway. So what do you mean? it's computationally heavy. It is computationally heavy, but they are being implemented, and you need to understand that even the hardware is advancing along with the software. So in like 5 years and 10 years, you have the hardware advancing in a very rapid pace. So even if the algorithm is computationally heavy, the hardwares can support that kind of computation. They haven't implemented in space robotics yet, because space robots are still very new to autonomy, but they are developed on robots on Earth already.
Okay, the next question is, given the limited power supply in the space station, sending battery-operated drones and robots poses a challenge. Can nuclear reactors be used in space stations to generate power? It's an
In space,
interesting question.
yes, that's a very interesting question, and that's something I cannot answer as an engineer, because nuclear power, of course, nuclear power is important, but space station are usually where humans live, and the policymakers would, and even the space agencies, they would never have nuclear and humans at the same place, because stations are not that big. It's as big as a football playground, but you cannot have nuclear power and humans working together unless you are very, very sure about the safety. So for Moon and Mars, we will definitely need nuclear power, because solar power is not so reliable, and you cannot function more than 14 days on the moon. So the robots by China, the robots by USA, they already have nuclear power RTGs, so radioisotope thermal generators on board. But having them on the space station is still a question that the policymakers can answer. For
Yeah,
engineering, yes, it's already developed. It can be implemented. Yes. Yeah.
okay. And the next question is, what are the potential advancements in robotics that could revolutionize space exploration in the near future?
I think I already kind of
Uh,
addressed
You
that
covered.
by modular robots
Mhm.
slide. So this is, I believe, is one of the very potentially groundbreaking uh, thing that will happen if you can have reconfigurable, self-repairing, self-recognizing robots, where they can change their shapes and they can do different kind of tasks, assemble themselves, assemble others, and adapt to the changing environment. That's what would be uh, really, really like groundbreaking and bring a lot of changes. So yeah, this is my answer.
Yeah. And the last question is from me. Any suggestion or guidance for all of us that can make us the space robot designers?
Space robot designers, yes.
Yes.
So I already told, like, if you are from data science background, then these are different things that you can do, mostly in the training and analysis and programming side of it. But if you are into mechanical and designing of it, then you should know SolidWorks, then Fusion 360, these kind of softwares, and be able to design really exciting kind of designs of robots. Like, for example, this slide, if you see here, this one is developed, modular robot developed by NASA. And these are different modules that attach to each other, and they become like habitats, sometimes into space, solar power, like solar towers, and different kind of infrastructure can be built with these modules. Then this robot is a legged plus wheeled robot. So it can change into legs, and then it can also change into wheels based on where it's able to where it's operating. And here, for example, this one is a like a spider inspired robot where it's moving with its leg, but then it can also be attached to a mobile robot, and then it becomes arms, and it can do different kind of manipulation tasks. So you need to be very innovative and think about what different challenges and tasks that are there and how you can solve them. So the skills that you can develop is this: be very proactive, very like innovative, and think more and more in a way how you would like your autonomous robots to work.
Okay, and I'm not seeing any question here in the chat box. This is your beauty, ma'am. You discuss this topic so well that no one has any doubt. And we truly appreciate insights in addressing these queries. Thank you, ma'am. Thank you a lot.
Thank
And
you very
over to you, Kamla.
Thank you, Raju, for your fantastic work in moderating the questions and keeping the discussion engaging. Um, Ma'am, I just have one question. How can space agencies and policymakers leverage the advancements in space robotics to enhance the diplomatic relations in space exploration?
Okay, that's a very interesting and complicated question. So mostly the space policies develop as the technology develops. So for now, space policies are different for different countries. For example, USA has a very advanced space policy for the companies that are working on space robotics. So NASA, for example, works very closely with all the space robotics companies like Astrobotic, Intuitive Machines, Astrobotic, and Gitai, and other companies. SpaceX also, they work very closely with NASA, and they are basically developing the robots for NASA. However, in India, it's different because in India, ISRO is the one that develops all the systems, because our private sector is not yet that mature to develop robots. Even for Earth application, you don't see that many robots in India, unlike Japan or USA, where you have robots deployed in military, in disaster sites and everywhere, and even in the entertainment and restaurants and everywhere. It's very common actually here in Japan to see robots around. So your policy develops depending on how your society or how your technology develops. So for example, my generation and your generation is now working on this kind of technology, developing advanced robotics. And as we become more and more mature to develop these kind of technology, the policies will evolve. The government will work on these policies, make them more adaptive, make them more easier to work with commercial companies. So I believe that's how it will happen. It will take some time depending on how you or I develop all of these skills and develop all this technology to be good enough to be deployed in extreme environments. And yeah, that's how we can collaborate with government. I hope that answers your question.
Yes, ma'am. Thank you so much for providing a very detailed and insightful answer to my question. And I could also see a question in the chat section. Uh, in context of current missions from different agencies on this same planetary body, can the different robots communicate with or warn each other regarding any hazards apart from their respective landers and satellites? Any such technology implemented?
Okay, that's a great question. As of now, the robots cannot communicate with each other, even if they are on the moon together at the same time. because they are at different locations. But in future, if we have more and more robots being in the same location, or say within 50 kilometer or 100 kilometer radius, there are multiple robots, they should be able to communicate with each other. So there is this infrastructure being built by NASA called LunaNet, and also by this European Space Agency, Moonlight, is where they are trying to develop GPS kind of systems, like a network of satellites that can communicate with the on-surface robots and also communicate with each other. So they would be like the orbital control stations. And also, if NASA's spacecraft or India's spacecraft or European spacecrafts are on the surface of the moon, they can be able to communicate with each other. This communication depends a lot on interoperability systems. So yes, if the countries or if the agencies have good communication between themselves on Earth, and if they have like good relations, then they will definitely develop the systems to be interoperable. However, for example, if it's China versus US or Russia versus US, due to the geopolitical conditions, current geopolitical conditions, it might be difficult and they might not be able to communicate even on Earth. So they do not develop interoperable systems and they will not be able to communicate on the moon. So that's how it works, unfortunately. But I hope in the next 10-15 years, when we have more and more robots, we will be able to also help each other and communicate with each other, inform each other of the different hazards and different landscapes that they are operating in. Yeah, that I hope that answers you, Mihir.
Yes, ma'am. So, ma'am, we just need to take over the screen to share some additional content. Could you please allow us to do?
Sure.
Thank you, ma'am.
Thank you, Kamla. Thank you, ma'am, so much for taking up all the questions so patiently and being so all the ears for all our curiosities. Thank you so much, ma'am. It was really a great and engaging and a very insightful session. So, we are now inviting all the space curious minds to join our club for delving deeper into the mysteries of the unknowns of the space altogether. Nebula Pioneers is always there to welcome you all for the journey beyond on LinkedIn, Instagram, Twitter, and WhatsApp. The membership form for our club, alongside the link tree for all our social media handles, has been posted in the chat window for your convenience. Request all of you to kindly go through them once and become a part of Nebula Pioneers. After all this time, as we have slowly approached the closure of this session, I would like to invite Kamala to take over the dais for vote of thanks to our esteemed guest speaker and the conclusion. Over to you, Kamala.
Thank you, Agamani. As we draw today's session to a close, I want to express my sincere gratitude to everyone who made this event a success. First and foremost, a heartfelt thank you to our distinguished keynote speaker, Dr. Shreya Santra ma'am. Your insightful presentation and expertise in space robotics have truly inspired us and expanded our understanding in this fascinating field. We are incredibly grateful for the time and knowledge you have shared with us, ma'am. Thank you, ma'am. To our
Thank you very
participants,
having me, and all the best to everyone and all the best to Nebula Pioneers. Be passionate and keep working hard. Thank you.
thank you, ma'am.
Thank you, ma'am.
Thank you,
To our
ma'am.
participants, thank you for your engagement and thoughtful questions. Your active participation made this discussion vibrant and enriching. Lastly, I want to extend my appreciation to the entire team of Nebula Pioneers. for their hard work and dedication in arranging this event. Thank you once again, all, for your participation and support. We look forward to seeing you at our future events. This is Kamala signing off. Until next time, have a wonderful evening. Thank you.
Does the meeting is over?